start the recording. So, Matt, take it away.
Okay, thank you. Welcome everyone. So let me share my screen. I hope this is visible. Okay, so yeah, my full name is Matthias Beck. People call me Matt, and all of you are welcome to do so. My day job is at San Francisco State, but I'm spending this year, and actually this past year, I spent this past year in Berlin. So I'll be here still until this summer. So this is actually a screenshot from my website. So embarrassingly enough, it's easy to Google. And one reason I wanted to, well, this is a partial screenshot. One reason I wanted to put this up is because there are two books here that are freely available on there, where you will find a lot of the sort of background of what I'm going to be talking about. So yeah, feel free to go there and download PDFs, and you'll see the connection. Let me tell you sort of like what my plan is for the 5 days. So the plan for today is to just give you sort of a feel for what I'm about to do. I'll give you sort of 3-4 sample classes of polynomials that I find interesting, and where the kinds of questions I want to ask will be interesting too. Day number 2, so I come from sort of geometric combinatorics with some non-trivial overlap in number theory, combinatorial number theory. And so day number 2, I'll give you a crash course in Erhard polynomials. This is like my main tools. Day number 3, I'll do another crash course sort of in triangulations and hyperplane arrangements and how they relate to Erhard theory. And then day number 4, I want to sort of relate that stuff to sort of slightly more general problems coming from semigroup algebras. And then, this is not set in stone. I might move some things, and we might take longer with some things. And so, for now, I plan to have sort of a day number 5 for sort of applications and other things. But let's see. Yeah, let's just see how this goes. But sort of like the general theme, and you will see this already today, actually. Yeah. So here's sort of like my world. Here's me. Yeah. So this is like, there's polytopes in here, and Erhard polynomials and good stuff like that. And sort of what I really like to do is not stay in this world. Yeah. So what I really like to do is, here's your world, whatever that might be. And if we're lucky, we can sort of talk. And so lucky, you'll see what lucky means. Yeah. But basically, I need to find some polyhedra. Luckily, polyhedra are given by linear systems, so that's those are in many worlds. Yeah. And then I yeah, so, again, if we're more lucky, we have sort of an interpretation in terms of Erhard polynomials and the kinds of counting functions that appear in my world. And what I'm really interested in is in these connections. Yeah, so this is not just one connection, but hopefully many. I should say from the get-go, you should feel free to interrupt me at any point whatsoever. I will also, ask for questions and so on. So, yeah, so just feel completely free to yell or chat or whatever. And I also wanted to make a remark about the research problem. So I will introduce research problems as we go along for the next 2 weeks. And they will all be of the sort, here is some interesting topic, go and play. Yeah. And so I feel rather strongly that sort of my job is to open the door, with some room full of instruments. I like to play music, so I open the door with a room full of instruments, but then I let you experiment with that, and you'll see what I mean by that too. Yeah. So, and of course I will write these up sort of again as we go along and post them on Slack, so you get a pretty good idea of what possible research topics there are out there. Max and I will also prepare exercises, and in fact, a few exercises for today already on Slack. These exercises are not a must. They're mostly sort of to get you a feel for the stuff, and to get your hands dirty. So yeah, so same thing. Go out and play. They're most fun as usual in mathematics to do with other people. So you should do that. Okay. Let's get started. So this is my first class of polynomials. So chromatic polynomials. I'm sure all of you know sort of the story. There's something called the four-color theorem, which used to be a four-color conjecture. Yeah, and so the four-color theorem says if you give me any map, you can color this map in 4 colors. And so there's a graph theory interpretation behind that, and so you see one example over here. This is the districts of Berlin, where I live right now, and so you make the countries or the districts, you make these nodes in a graph, and you establish an edge if there's 2 countries that share a border. And so this becomes the coloring maps now becomes a problem of coloring the nodes of a graph. And so, yeah, so I want to think about this as yes, so you have a graph. Maybe let's start with that first. Yeah, so you have some graph T with nodes and edges, and so you have a coloring function that goes from V into, let's say, the integers. Well, later on we're going to have n colors, so maybe let me just right away say, okay, whenever I say this, I mean a set from 1 to n. Yeah, and so I'm really interested in proper colorings, and this means that if you have 2 adjacent nodes, the colors are distinct. Yeah? And so it turns out, and again, most of you know this, the planar maps correspond to, maps correspond to planar graphs. Yeah? And so the four-color theorem is a theorem about planar graphs. It says that you can get such a proper coloring for any planar graph when n is 4. And so there's a story. It's a good story. If you don't know the story, you should read up on it. About the four-color theorem. It was a conjecture, and then people thought it was a theorem for about 12 years or something like that. And then somebody found a mistake, and then it was a conjecture for another 100 years. And then it was proved. It was the first sort of like serious math proof that used computers. And in fact, the only proofs that we have today use some sort of computer search. So you see, first chance of being famous, find a proof of that theorem that does not need computers. It's an open question. Anyway, I'm not doing that now. Yeah, but so what's the connection to what I'm doing? So sort of Birkhoff came along and wanted to prove this four-color conjecture at the time, and he said, "Okay, let's generalize this." So let's say, so this is what's now called the chromatic polynomial. So he said, let's consider the number of such proper n colorings. N colorings of the graph. And so the idea is, okay, if I can understand this counting function, then I can try and plug in 4 and G as a planar graph, and therefore have solved the four-color problem. So this didn't work out for Birkhoff, but what he did was still good, So because he realized that this is a polynomial. So this is sort of one of those. This is one of those more famous sort of polynomials in combinatorics. And so so this monstrous polynomial of degree 23 that I wrote down here is for the Berlin map. And you should you're welcome to plug in n equals 4, and you will see that there's a non-zero number, which I forgot. It's a pretty big number. So I'm sure many of you again know this chromatic polynomial, but I want you to imagine for a moment that you don't know that this function is a polynomial, because I want you to appreciate the fact that this is a polynomial. So it's not a deep statement that this counting function is a polynomial at n. But again, if you imagine that you don't know this, there's something magic in here. So we're counting something, so somehow you realize that there's this counting function has a structure of a polynomial. So let me I sort of can't help really. Let me show you my favorite way of proving that this is a polynomial. Is you consider the following fact. So again, I want to think about certain functions from V to N. So namely the colorings, right, that are proper. And so what I'm going to do now is I'm gonna make a commuting diagram out of this. So I will first think about surjective proper colorings. So up here I just have proper colorings. And same thing here, okay. So this is the same map, except that I'm requiring you to use every possible color. And so, and then, so you know, K is less than or equal to N, yeah, so, and then we're gonna complete this diagram by now, you know, mixing up those K colors among N colors, yeah, yeah, so here I'm just saying, okay, you're not allowed to use just the colors 1 through K, but I'm allowing you to use the colors 1 through N, but I'm only going to use K of those N numbers. Yeah. So what, you know, why is this useful? Well, you know, down here, yeah, so for you know, for a given K, you know, this is some, there's some finite number of things, yeah. So this is a finite number over here, and let's give this a name, maybe C sub K. You know, so for every K, if I want to say surjective colorings, that's just some finite thing. And then over here, I hope you agree, the number of sort of distributing K colors among N, there's, you know, N choose K many ways. You know? And so this gives you now an expression of the chromatic polynomial. Namely, I can write this chromatic polynomial now in terms of these numbers CK. And I guess my K runs from 1 to the number of nodes, because if you want to have a surjective coloring, you can only go that far up. Yeah, and so what you have staring in your face here is a polynomial. It's written in a funny way. Yeah, so but you have some coefficient CK times an N choose K, and as a function of N, this is a polynomial. Okay. This would be a good time to break for questions. Who's brave enough to ask the first question? Let's see. If you don't have a math question, you can ask about my dog.
What's your dog's name?
Kumi. Good question. And you might hear her at some point this week. She's very social. Okay, so this is suggesting something, and that is, if we look at polynomials in combinatorics, there's different bases that we might be interested in. Yeah, so yeah, so there's you know sort of like, so okay, I want to think about polynomials in N. Yeah, so I want to think some polynomial in the variable N. Yeah, so there's, of course, there's the standard basis in terms of monomials. Yeah. But you just saw a different basis, and for reasons that will become clear maybe only tomorrow, I would like to write these binomial coefficients that you saw for the chromatic polynomials like this. Yeah, so I would like to think of N minus 1, choose something. Yeah, so this is another basis. And there's a third one. So this now I'm going to have to fix a degree. So over here, I now have to say this is a degree less than or equal to d polynomial. So I do n choose d, n plus 1 choose d, up to n plus d choose d. And yeah, we'll be working in all of these bases. And you can see sort of an advantage for the chromatic polynomials already. Yeah, so when we write the chromatic polynomial in the first basis, I claim that the coefficients will always alternate. Yeah, so this is useful. Yeah, so you saw this over here. So my coefficients of my monster polynomial over here, they go plus minus, and that's not an accident. That always, this is always true, and you can try to prove that. This is not super deep. Yeah, over here I have some interpretation, right? So in the second basis, I have an interpretation. So I guess I have to shift, right? So in the previous page, I had a basis n choose k, and so now I have the basis n minus 1 choose k, but okay, that's just a shift in n, a finite shift. And in my last basis, there's also an advantage. So I claim in my last basis the coefficients for, if you write the chromatic polynomial in this last basis, the coefficients are non-negative. Yeah, so this is true, by the way, in my second basis too, because we have a counting interpretation. And so, yeah, so where is all this going? By the way, the fact that in your last basis you have a non-negative coefficients is not entirely trivial. But again, you can try to prove that. Yeah, but so where all of this is going is I guess my question of the week. Yeah, sort of like so okay, can you classify, let's say, chromatic polynomials? Yeah. And I'm not just going to ask this question for chromatic polynomials, but we'll ask these questions for several polynomials. Yeah, and I put Herb Wolf's lovely book titled "Generating Functionality" on there. Number one, because it's related, but number two is apparently he sort of was famous for this question. He liked this question a lot. Yeah, so I'm asking a classification problem. So, I'm asking, give me your favorite polynomial. And then, let me try to come up with a graph that has your favorite polynomial as the chromatic polynomial. Yeah. Or tell you why that's not possible. So if your favorite polynomial doesn't have alternating coefficients in the standard basis, it's not going to be a chromatic polynomial. If your favorite polynomial has a negative coefficient in one of the other two bases that I just showed you, again, your polynomial is not chromatic. So these are necessary conditions. It's sort of ideally what I'd like to have is necessary and sufficient coefficients, and we're super far from that in the case of chromatic polynomials. Yeah, so so what that really means is, like, when I ask sort of classification problems like this about polynomials that appear in combinatorics, I mostly ask about sort of partial classification. Can you tell me something? So for example, all of these things that I'm writing down here are sort of, towards a classification of chromatic polynomials. Let me give you just a sense of that. This is sort of part of recent research. So there's a quite famous theorem of Junhe from I think 2012, who showed that if you take the coefficients in basis number 1, then and you forget about signs for a moment, then the coefficients form a unimodal sequence. So this was an old conjecture, and it was quite a splash when June proved this, actually, as a graduate student. Sort of, yeah. So this is the type of question I want to ask. So like most of the polynomials that I'm going to show you are not classified, and so then the question is, can you tell me something? Let me give you another one of my theorems, and in fact, I will give you an idea where this theorem comes from this week. So this is not yet published, actually. It's on the archive with Emerson Leon. So what we proved in basis number 3 is that the coefficients in that basis, so I like to write these coefficients in the third basis with a star. The coefficients in that basis are sort of partially unimodal. So I can so I can do the first part. So we go to the middle, and the middle for us is d plus 1 over 2. And so we can't quite prove that afterwards they're going down, because sometimes they don't. But at least that first half goes up. And so so this is one of the things that I want to show you is like, okay, there's a theorem about chromatic polynomials, a theorem about graph coloring, but I will prove this in my world. So I will show you how one can prove something like this using geometric combinatorics.
Sorry, Matt.
Yes.
Can you maybe say what unimodal means for a sequence? Because I'm not sure.
Yeah. Thank you. So if I have a polynomial like my chromatic polynomial, so it doesn't have a constant term, but let's just pretend it does. Then there are some coefficients, and let's say I have degree n. No, n is my variable. I have degree m. And then unimodal, it's supposed to be an A, means my coefficients, they go up to some point. I don't know what that is, and then go down afterwards. So think about one row of the Pascal triangle. So if you look at the binomial coefficients in one row, they form a unimodal sequence. They go up and they go down. There are other questions. And so what I'm saying over here, so this is sort of in our theorem, you sort of stop, you go up to some point and then you don't say anything else. Yeah, so that's what I mean when I said sort of like these are sort of half unimodal. Other questions?
I was wondering if you take the set of all the chromatic polynomials, do you know if it has a certain structure, an algebraic structure of some kind?
An algebraic structure, yes, there's some algebraic structure. And in fact, we will talk about this. I sort of mentioned this later on today, but we will talk about this more on Wednesday.
Okay.
Yeah. I can give you some buzzwords. So what I'm about to do is show you some Ehrhart polynomials, and Ehrhart polynomials are Hilbert polynomials of certain algebras. And we can think of a chromatic polynomial as a sum of Ehrhart polynomials. So the algebraic structure for chromatic polynomials is you can't quite write. You think of them as a Hilbert polynomial of some algebra, but you can think of them as the sum of finite sum of Hilbert polynomials. Yeah. I hope that goes a little bit in the direction of your question.
Yeah, thanks.
Yeah,
I have another question.
Yes, please.
What about Tat polynomials for matroids? What do we know? And does the same question make sense?
It's a good question. So it's a good question, and that's as far as I know a playing field in terms of what I'm going to show you this week. But I want you to keep that question in the back of your head. Yeah. So for those of you who don't know Tat polynomials, they are sort of a generalization of chromatic polynomials. It's a vast generalization actually. But what makes them quite different is that they are two variable polynomials. And so, in terms of two variables, things, what I'm showing you this week can still be done, but it's much harder. So somehow, sort of that I have one parameter here, this n is somehow important. But that doesn't mean nothing can be done. Yeah. So I forgot who asked the previous question. Yeah. So this interpretation in terms of chromatic polynomial as sum of Ehrhart polynomials or sum of Hilbert polynomials, these are all things that people figured out in the last 15 years or so. So this is all relatively fresh in mathematical historical terms. Yeah. So I like the question about Tat polynomials a lot. And yeah, so I have some ideas, but it's probably maybe too early still. Yeah, so if you have some good ideas how to apply these things for Tat polynomials, I would like to know.
Thanks.
Other questions? So we're about to have a coffee break. So let me start Ehrhart polynomials after the coffee break, and instead give you one more motivation to look at different bases. Yeah. By just giving an example. So if you think about this basis over here, right? So again, what does that mean? So that means, for example, for a chromatic polynomial, we're going to write this as a sum. So sorry. Yeah, so maybe let me use A's now, right? So this is like a which way do I want to go? I think I want to start with the last one. So I'm going to write this as A naught n plus D, choose D. And then A1. Yeah, and I guess those A's are related to, those are my chi-stars. Maybe I should have just used chi-stars. But anyway, so what's the point over here? Yeah, so let's look at one of those binomial coefficients as a function of D, right? So as a function of D, let me write this as 1 over D factorial times n plus D n plus D minus 1, and so on. And I guess the last term here is n plus 1. Yeah, but I can do the same thing with the other binomial coefficients. And you can now smell like what, what's the nice thing about this particular basis is you can read off the roots, at least of one term. So this term over here has a root at, I guess, negative D plus 1, and so on down to negative 1. And the next term has a root at negative D plus 1 and negative D plus 2 down to 0, and so And so this makes it super easy to, for example, plug in things like n equals 4. So that was that was the 4-color theorem, right? So if now my graph is planar, then I claim this is a good basis actually, because if you want to plug in n equals 4, we don't have to worry about this last term over here, unless D is super small. This is going to be 0. And so for n equals 4, what that really means is you can just concentrate on, the first, I guess, 5 coefficients, correct? And so in this basis, if you're interested in the if you're interested in the 4-color theorem, in this basis that really says like, you're interested in the coefficients A0 through A5. You can prove that one of them is non-zero. Well, yeah, actually that's enough, right? Because the coefficients are non-negative. So if you can prove that one of them is non-zero, you prove the 4-color theorem. Yeah, so these different bases have advantages beyond sort of classification problems. That sometimes, in some instances, they're super practical actually. Okay, so why don't we take a coffee break and we'll continue in 10 minutes. There any questions that came up over coffee? Okay, so I want to switch gears and tell you one of my other favorite problems. This is a polytope question. So you take the set of all doubly stochastic matrices. So this is take n by n matrices, non-negative entries, non-negative real entries, such that each row and each row and each column sums to 1. So they're called doubly stochastic for a reason. You can realize that that's a polytope. It's a famous polytope. It's called the Birkhoff-von-Neumann polytope. It's a polytope because, for example, it's given by linear constraints, correct? Yeah, so all my constraints are linear. So I have non-negativity constraints, and then I have some equations. And so a natural question is, what's the volume of this polytope? So it turns out this is not full dimensional, but there's sort of like relative volume that you can define, and then in fact you want to sort of normalize that, and sort of here's what's known. Okay, so these are the first 10 volumes, yeah, and that's all we know. Yeah, so it's yeah. So if you look at these numbers, they look a little bit like, you know, randomly generated, maybe except for the last couple of digits, and that's what I see too. Yeah, so there's no clear whatever pattern of prime factorizations or something like this. You know, yeah. So this relates to my next set of polynomials. And these are Erhard polynomials. Yeah, so it relates to these kind of volume problems. So I'm starting out with a polytope. So polytope P. So this is either, you can think about this as the convex hull of a bunch of points, yeah, and I think of these as column vectors, and I will often write this as a matrix, yeah. So let's say I have, you know, m points in d-dimensional space. So for example, you know, if your favorite polytope is the cube, then that's the convex hull of these 8 points. Or you can think of a polytope as given by a linear system of equations and inequalities. Yeah. So let's say we're in R to D. Yeah, then I think of my polytope as given by just like linear algebra, by a system of equations, except I'm allowing inequalities now. Yeah, so yeah, so when I say less than or equal over here, I mean component-wise. And so if you've never dealt with a polyhedra, then this is not obvious that those kind of two descriptions give you the same set of objects, but that's a theorem. Yeah, this is so like the fundamental theorem of polyhedral combinatorics, or discrete geometry, if you want. Yeah, is that any such convex hull can be written as a solution set to a linear system of inequalities, and any such solution set, as long as it's bounded, is the convex hull of finitely many points. And so now, you know, so like the question I just asked on the last slide is, you know, what's the volume? Yeah, and so yeah, so what I mean is by this is just, you know, Euclidean volume. Let's assume that our polytope is full dimensional. Then yeah, so I can think of this as like a Riemann sum kind of thing, where, you know, I take my polytope and intersect it with little boxes, or you can just think of stuff like integer points that I then scale down by n. Yeah, so this is, yeah, so this is, you know, pictured over here. Yeah, so I think of if I take this grid picture on the right and make my grid smaller and smaller and smaller, and I keep counting points, and I get the volume. I guess I have to normalize too. So yeah, so I have to better divide this by 1 over n to the d. And so now, yeah, I'm a combinatorialist, so now I forget about this limit over here and just say here's a counting function. Yeah, and I call this the Erhard counting function. So this is, think of this now n as just a parameter. And so now this becomes a counting problem. Yeah, and if I can somehow solve this counting problem, then I can take a limit and answer this volume problem. And so, yeah, so the main theorem sort of in my world is, so this is Erhard's theorem. This is from 1962. Erhard's theorem says, like, if my polytope has integer vertices, so this means that these thing over here as a matrix, if you want to, if this lives in z to the d by n, so if your extreme points, the vertices of your polytope, if they're integers, then this here is a polynomial. Okay. So yeah, so number one, what does it mean? Well, here's another class of polynomials that I'm trying to understand. But maybe before that, we should ask the same question as sort of like this, my magic question about chromatic polynomials. Yeah. So just like with chromatic polynomials, this is not obvious that you have this polynomial structure, and in fact, it's actually much less obvious than in the chromatic polynomial case. Yeah. But if you go back to the volume, the volume question is, then you should say, like, wait, well, this is like, sort of amazing, because a polynomial is given by a finite set, is a structure with finitely many data, right? So to know a polynomial, you only have to know, if your polynomial has degree d, you have to know d plus 1 pieces of data. Yeah. And so essentially this theorem says that we don't need to do analysis. So this theorem says, like, old Riemann said, you have to take a limit over here to compute this polynomial. And Erhard says, no, actually, you don't need to do that. At least if your polytope has integer vertices. So it's, it suggests that, for example, this problem of computing this volume over here is really not an analytic problem. You can approach this combinatorially. So if you just know enough data points of the Erhard polynomial of one of those polytopes over here, then you can compute the volume from those data points. So there's, just like in the chromatic polynomial case, there's some piece of magic in here that I would like you to appreciate. Okay, so maybe let's go back into our, we had these polynomial bases. So we'll write them down again, but you remember there's 3 of them. The first one was just sort of in standard monomials. It turns out that's not a super interesting basis for Erhard polynomials. The other two bases are interesting is because here you have non-negative coefficients. Which is not true in the first basis. The first basis, like I said, the first basis is in some sense maybe not the right basis. And just again to give you an idea of this is fairly recent stuff. So in the second basis, this is a theorem of Felix Breuer from 9 years ago. In the third basis, there's a famous theorem of Richard Stanley from 1980. And so once you have non-negative coefficients, there's sort of lots of questions you can ask in combinatorics. So now, so this somehow suggests if you approach this sort of from combinatorics, those two bases, number 2 and 3, are your friends. And in fact, so here comes my first research problem. It's like I said, it's vague, but there's a big playing field. So these coefficients are called they form what's called the F star vector of the polytope. And so here's one research problem for next week. We'll play with this. So I claim this is not that much studied, and I'd like to encourage you to do so. So the coefficients in the third basis, they're called the H star vector. And they're sort of older, these coefficients are older, and they're a little bit better understood. There's open problems there too, and we'll get to some of them there. So this will come tomorrow and on Wednesday. But so the F star vector is kind of like, it's a little newer, and I'll be more precise when I write up my projects. But so here's project number 1. And I will outline proofs tomorrow of why these coefficients are non-negative. And we'll see some special cases. Are there any initial questions about Erhard polynomials?
I don't see any, but may I ask what, I don't know if you already want to go into that, but what the F star vector, I'm familiar with F vectors, like counting faces of things. So what would be an F star vector be counting? If you have a short answer for that.
So I can so there's an F star vector and H star vector, and like Alessio is saying, most of you know of F vectors and H vectors. So the reason for this notation, well, one reason is that if your polytopes are very, very special, then they have what's called a unimodular triangulation, whatever that is. It's a special kind of triangulation, and we'll talk about those on Wednesday. And the triangulations have F vectors and H vectors by counting faces in the triangulation, okay? And if your polytope has a unimodular triangulation, the F star vector is the F star vector of the polytope is the F vector of the triangulation, and the H star vector of the polytope is the H vector of the triangulation. So in particular, in those cases, the fact that your coefficients are non-negative are actually facts about triangulations. Yeah? But the magic of these two theorems is that you don't need these very, very, very special polytopes that have unimodular triangulations. Yeah? Those coefficients are always non-negative.
Okay, thanks.
Good question. Other questions? Okay. I want to make a connection to chromatic polynomials. Okay, so yeah, to do that, I need to look at a directed graph. Okay, so a directed graph has again nodes and arcs now. Yeah, so this is now a directed graph. And directed just means every edge now has an orientation, either this way or that way. Yeah, and so again, I wanna sort of define a proper coloring. Yeah, by adjusting my definition of a proper coloring of the of an undirected graph. Yeah, so for an undirected graph, if I have an edge between whatever u and v, then for the undirected graph I said, okay, the color at u cannot be equal to the color at v. Now I have a directed graph, so my edge has some direction. Let's say it goes this way. Yeah, and so now I'm going to demand that my color at v is strictly bigger than my color at u. Fair enough. Okay, and so out of such a thing, I can make a polytope. Yeah, so out of this, let's call this the polytope that belongs to the directed graph. Yeah, so let's say I have a directed graph on, let's make it D nodes, yeah, because that's going to make my polytope D-dimensional. Yeah, so I'm going to look at all points for which each variable is between 0 and 1. So I live in the D-dimensional unit cube. Yeah. And I have this condition. Yeah. So if I have, so this comes from my graph. If I have, an edge that's directed from u to v, then I want, the coordinate indexed by u to be less than the coordinate indexed by v. Yeah, so this is a polytope. Well, it's defined by strict. There's a strict inequality over here, right? So, okay, we can do that. So let's make these inequalities also strict. So let's say each coordinate is strictly between 0 and 1. Yeah. So now this is an open polytope. Yeah, so it's defined by strict inequalities. Okay, so that just means my polytope doesn't have a boundary. Yeah, and so okay, what's the connection? Yeah, so if I now let's keep green over here. So now if I want to say, okay, let me compute sort of the chromatic polynomial of this thing, right? So yeah, so that's again, a number of proper n colorings. Well, then, what does that mean in terms of my polytopes? I claim, you're counting exactly integer points. Yeah, so this is this Erhard function for the polytope. And I have to have to sort of dilate my polytope or shrink the lattice by n+1. Yeah. So what's the connection over here? So, this is kind of like, this means, we're going to replace this 1 by an n+1. So, each coordinate is now strictly between 0 and n+1. Yeah. Well, that means that each color is between 1 and n, correct? Yeah. So for a directed graph, sort of this chromatic, polynomial kind of thing for a directed graph is an evaluation of an Erhard counting function. And I claim this polytope has integer vertices. So this is an Erhard polynomial. Okay, so all right, so what about chromatic polynomials, right? So what about your graph? Well, so I can write this. I can write all of my colorings of a graph as one possible coloring of one possible orientation. Yeah, so I can think of my chromatic polynomial as being, subdivided into colorings according to orientation. Yeah, and so as long as my D now ranges through all orientations of my graph, I get the chromatic polynomial. And so now you can see what I said about half an hour ago. So this is now, this is not quite an Erhard polynomial, but this is a sum of Erhard polynomials. Yeah. Sorry, I need to. No, it's the way I wrote this is okay. Yeah, maybe it's better to say, okay, I have an open polytope over here. So anyway, it's a sum of Erhard polynomials. Yeah. And so this was my first slide, right? So when I said, okay, I'm gonna try to make some connection to some other areas.
Matt, I think there was a question.
Yes, please.
So is it trivial that a proper coloring of an undirected graph is a proper coloring for some of for a possible orientation of the graph?
I don't like the word trivial, but I'll tell you why that is true. So if you give me a coloring, if you give me a proper coloring of your graph, and you now actually think of the colors as numbers between 1 and n, then this induces an orientation. Simply by saying, whenever I see a number going up along an edge, I will orient that edge accordingly. And so that makes it that, so you can think of the set of all proper colorings of your given graph as partitioned by proper colorings of the possible orientations of your graph. Okay. Does that make sense? Because once I put down a coloring on your graph, then it's proper, then that induces an orientation. Yeah. If I look at an edge and one node has color 3 and the other one has color 5, then my orientation has to go from 3 to 5.
Yeah, okay, thanks.
It's a good question.
So there is a question by Sasha in the chat. So I'm going to read that. Is there any symmetry between the chromatic polynomial for one orientation D and the one with all arrows reversed?
It's a good question. In general, I believe no. In general, I believe no. that can be quite different, actually, those things. Yeah. It's a good question. Let me make two remarks along along that question. Okay, so you can ask, okay, like, you know, before I asked Sasha's question, ask, okay, are all orientations possible? Yeah. And the answer is no, actually, right? Because you can't have a coherently oriented cycle, right? If I have a cycle where all the edges going in the same directions, then I'm saying this color is bigger than this, which is bigger than this, and so on, and get to a contradiction. Yeah. So in fact, you won't see all. You know, I mean, for those orientations with cycles, my Erhard polynomial is just going to be 0. Okay, so I can write this sum if I want to. Yeah. But so it turns out you can restrict yourself to what's called an acyclic orientation. Yeah, so one that where there's no cycle. And go back to blue. So those acyclic orientations, you can think of them as posets, partially ordered sets. Yeah, once you don't have a cycle in your directed graph, then you know you might as well draw your directed graph in such a way that all the edges look up. Yeah. And so in fact, sort of what I'm computing over here, so what I'm computing over here is there are Erhard polynomials that are somehow attached to posets. They're called order polynomials. So now you can, what this suggests is you can play a game here, not on graphs, but on posets. Yeah, or if you want, acyclic directed graph. Those are the same things. Yeah, and I believe Sasha's question now says, if you give me a poset and you compute this order polynomial and you take the poset and turn it upside down and compute that order polynomial. Those are, I think, quite different concepts. Good question, though. Yeah. So those, I'm grateful for the question, because order polynomials, they are important as they're a very small class of Erhard polynomials, but they're an important class because they give you lots of interesting examples. Sort of order polynomials, you know, there's lots of directed graphs out there, you know, or posets, and that suggests that there's a lot of order polynomials, and that class turns out to be sort of big enough to see some interesting examples of Erhard polynomials. Yeah, really only a small set of Erhard polynomials, but they're already interesting. And I might include a research project on order polynomials. Let's see. And more questions on this connection.
I think we don't have any more questions at the moment.
Sounds good. Okay. So I want to show you something, again, completely different. Yeah. And again, something where there's connections to the world that I live in. And it's the following thing. So you're starting out with a lattice. So, so this lives in some R to the D. Yeah, so this is, so a lattice you can think of as just a discrete subgroup of R to the D. You might as well think about it as Z to the D. Yeah, but there's so every lattice is isomorphic to Z to the D for some D. Yeah? So, you know, for practical purposes, think about it as Z to the D. And so now I'm going to fix a subset M. And I think of this as a generating set. As a semigroup. Yeah, so what I mean by that, so I'm giving you, I guess, sort of a picture on the right. Yeah, so this is Z2, and here's my origin. Yeah, so then you can think of, hey, take the standard unit vectors, right, and they generate Z2 as a group, correct? Any element in Z2 can be written as an integer combination of these two vectors, right? But so now as a semigroup, I'm only allowed to add, can't subtract, and so that's not enough. And so one such generating set might be the unit vectors and their negatives. But maybe you want to throw in more generators, right? So I can also think of, let's say these 6 vectors as generating Z2, and so why is this interesting? Yeah, so if you now give me this generating set, then this gives rise to what's called a word length function. Yeah, so this is a function on the lattice into non-negative integers, and it just records, for each lattice point M, let's say, a minimal way of writing M in terms of my generators. Yeah, so this word length function depends on both my lattice and the generating set. Yeah. So this is the minimum number of generators M needed to express, this lattice point. Yeah, so if you think about, this point over here, so it really depends on my generating set. So the generating set that you see right now, this orange point has word length function, 1. But if I didn't have those generating functions, now all of a sudden it has word length function 2. And so from this, we're going to compute what's called the growth function. Of the lattice, so maybe I'm going to call this G. And it's the number of lattice points with word length function n. So the number of lattice points for word length is n. Yeah, so for this growth function, there is exactly, so g of 0 is 1, so the origin is the only point in the lattice with word length function 0, and then g of 1 is the number of generators, and so on. And so, so this is what people are interested in. So you give me your favorite lattice. Often this is a lattice that has some applications. And you give me your favorite generating set. Again, this usually comes from application, and you want to compute this function. So some of you know some representation theory. So one thing you can do is you can take your favorite root system, and then consider the root lattice, so the lattice generated by your favorite root system. So, you know, if your favorite root system is, let's say, type B, we can draw this here, right? Then you're looking at the lattice, you know, z to the d generated by all roots of the form plus minus a unit vector, or the sum plus minus some unit vector plus minus another unit vector. Yeah. Okay, so does this make sense? So, okay, you know, where does Erhard, you know, polynomial come into place here? Well, okay, the polytope is, you know, the polytope that you might want to consider is sort of, you know, clear. You know, you want to take the convex hull of all your generators. Yeah, and so, you know, so, you know, where does this growth function come into play? Well, okay, so let's go back and do this over here. So, yeah, so I never quite said this, but so your Erhard polynomial, you can write like above, or you can think of, so in my definition here, I counted points in P in the shrunken integer lattice, but you can, you know, the same count you will get by leaving the integer lattice as is, and you dilate P. So n times P is just the nth dilate of your polytope. And so, this seems to be the right function here to look at, because, you know, twice my polytope, at least on the boundary in this case, has, you know, precisely the lattice points of word length 2. So Erhard now says, you know, if we're lucky, then this growth function is precisely, well, it's the point, right? The integer points on n times P, you know, take away the integer points on n minus 1P. So this makes sense. Yeah. So I have, you know, I guess here's P, and here's 2P. And so, so the points counted by G of 2 are sort of on this outer boundary. You can tell already from my picture when we're not lucky, right? I mean, so, okay, this lattice here and my generating set are super, super nice, right? But if the lattice is not so nice and I have some points sort of in between here, then it's not going to work, correct? And so this is now, this is now a structural question. So like, so what does this really mean? So the question is there a difference between, so there's two semigroups here. So the semigroup I'm interested in here is what some of you might want to write, ZM, right? So this is a shorthand description of saying, I'm going to take my vectors in M, right? So this is my generating set, yeah, and I look at all, sorry, I shouldn't say Z, I should really say Z non-negative, right? So taking all non-negative linear combinations of M. Yeah, this is exactly what I'm interested in. Yeah, but what does Erhard really do? Yeah, so Erhard says, okay, let's dilate first, right? Real dilates, and then look at the integer points. And I mean, this is a funny way here of come on. This is a funny way of writing z to the d, correct? So my second semigroup is just z to the d. Whereas my first semigroup is a subset of this bigger semigroup, and so in this in this case, everything's the same, and I can use Erhard theory to compute these growth functions. And it's an interesting part of Erhard theory. So it for example, if you do this now for the classic Coxeter root systems, these are super interesting polytopes, actually, it turns out. And their Erhard polynomials are non-trivial and so on. But it's also an interesting question is like, when does the setup not work? So, when you have a generating set, that gives you a lattice, it's isomorphic to z to the d, but it's not all of z to the d. It's like it's a sublattice, of some finite index, let's say. Any questions about this?
I have a question.
Yes, please.
So, what does this generating set M look like? Is there some symmetry we can assume?
No, good question. Good question. In practice, you will assume symmetry because in practice, M comes from something that you're interested in. But nothing stops you from taking this generating set. So right, and you can see your polytope changes, right? So oops, that was not good. Right, so this just changes the geometry, okay, and then so again, in my world, maybe this is kind of cool, right? So here's a nice little polytope. But yeah, so these word length function, they come from applications, and in applications often you have symmetry. Actually, it's good that you asked this question. So here is an important. This is sort of this is an important case of M that's not symmetric. You can do in any dimension. You take all the unit vectors and then the vector -1, -1, -1. Yeah, it's sort of symmetric, but not exactly. Yeah. So this turns out to be this also has applications, important applications. Yeah. And I was reminded of this by your question because this is sort of like a minimal set of generators, correct? If you want to generate this if you want to generate Z2 as a semigroup, you will need at least 3 generators, correct? And this is sort of up to isomorphism, I think this is the only way to do it with these three generators. And the same thing is true for z to the d. If you want to generate z to the d, I believe you need d+1 generators as a semigroup. Yeah. And so you can also, there's a polytope here, and it's very pretty, right? So it's like, this is sort of it's a triangle. It has some minimality properties, correct? It has exactly the origin interior. There's exactly one interior point, but it's otherwise it's kind of like as small as possible. Yeah, and so this is an important polytope, turns out, in general dimension again. Yeah. Other questions?
So Matt,
Mm-hmm.
I think we're a couple of minutes. I mean, we would be a couple of minutes over time, but since we started, I think 6 or 7 minutes late, you still have maybe a couple of minutes. But yeah, after that, I would probably stop the recording and go with the Q&A session. If you're okay with that.
I'm done with what I wanted to say. So well, I'm good. Yeah. I mean, the only thing I wanted to say about this slide still is so we'll do sort of a lot of this stuff on Thursday. Yeah. So when I look at sort of general, some more general semigroup algebras.
Okay, so Lorenzo, I think you can stop the recording then.